Welcome to this explainer. Let's dive right into the PN junction, the hidden physics literally powering your microchips.
So what actually happens when two oppositely doped semiconductors physically smash together? Let's figure it out.
We start with a single crystal split into P and N regions. That split, the metallurgical junction. Right there, a massive density imbalance forces electrons in holes to just wildly rush across the boundary. This leaves charged ions behind, creating an opposing electric field. It's basically a microscopic tug of war.
Now, in thermal equilibrium, the diffusion force pushing carriers apart perfectly balances the field, pulling them back.
Looking at energy bands, you'll see the Fermi level, our thermodynamic baseline, remains completely flat here. But notice how those conduction and valence bands literally bend as they cross that space charge region. That bending creates a built-in potential barrier. It keeps the peace by stopping majority carriers from crossing. Okay, so how do we actually calculate this barrier? Let's build the math piece by piece. Our puzzle kicks off with the standard thermal equilibrium equation for electron concentration. Then, we lock in the N region's electric potential using its Fermi level energy difference. Plugging that potential right back into our first equation reveals a beautifully clean exponential relationship. This neat trick lets us solve directly for the N region potential using just the donor concentration, ND. We use that exact same logic for holes in the P region, but with acceptor concentration, Na. This effectively isolates the P region's potential, based entirely on its specific energy level shift. And boom! With that, we elegantly solve for the final P region potential component. Combine those components together, and we get the absolute master equation for our built-in potential barrier. Pop in real-world silicon doping concentrations, and you get a tangible barrier of exactly 0.713 volts. Now, let's shift gears. How does the separated space charge actually build a powerful electric field? To calculate it, we unleash Poisson's equation. It's the ultimate math tool for linking charge to voltage. This perfectly illustrates how a one-dimensional analysis links volume charge density directly to electric field changes. By integrating all that constant charge density in the P region, the electric field mathematically takes shape. Pinning the field to zero at the boundary finally hands us our exact electric field equation. We've quantified this standoff. But what happens when an external voltage totally disrupts this perfect, delicate balance?